Hi, this is Jeremy Bryden from Core S Squared Software Solutions. Today we're going to talk about Cubism, which is a small experimental project we were working on to try and understand how a specific video game was able to render its scene. And we're talking about Minecraft, which is a very interesting game where the user is put in a world where all the world elements, so the world itself, is made of uniform cubes. It might seem kind of trivial, just render a lot of cubes, as many as you can, but it turns out it's much more difficult than you might think. Just imagine a small world where it's 128 cubed elements, so that's 128 by 128 by 128. Turns out, because of the exponential growth, as soon as you hit a certain relatively small number, it turns out that there's simply too many polygons to render on scene unless you start applying some smart solutions. So what we did was we tried to find these solutions to render as many cubes as possible, but do it in such a way where we don't actually kill the user's graphics card. So we started subsampling the world, meaning instead of treating the world as a series of small cubes, we actually treated the world as a series of relatively middle-sized chunks. So a cube, and you can see this in the background, is just the basic unit in the game. You could maybe break it or create a new one. From there, you could start building complex structures such as bridges or a building with them. But our chunks go ahead and takes a small size, 8 by 8 by 8 of these cubes, and applies an optimization algorithm on it. Any cubes that are hidden by other cubes, so if you have a cube that's hidden by 6 other cubes surrounding it, doesn't get rendered. Also, we only render the faces of those visible cubes that are actually facing air. So if you look at a cube from the side, you might not necessarily see the back face because it could be hidden away. So we go ahead and throw away those polygons. And we go ahead and start applying view volume frustum for these chunks. So chunks that are behind the user are never rendered, as well as chunks that are too far from the user aren't rendered either. So we created a small world that's about 128 by 64 by 64, and we experimented with these different rendering approaches. And we have a nice simple application that just shows a small world that the user can go ahead and fly around with in a no-clip version of the camera. Unfortunately, the frame rate dips here a little bit just because we're using some software capturing components. But you can see our world, just like Minecraft, is built by a series of uniform, discrete cubes. And if we go inside the world, because it's not reachable by air, we go ahead and don't render the inside, so the ground of the world. If you want to, you could also render the points and the polygon faces just to show you how many, and this is in brute force, to show you how many surfaces you would have to render in a brute force approach. Also, we implemented some basic physics. The user can go ahead and just walk around, jump if they choose to. The jump physics, the jump acceleration hasn't been pushed down too far, so the user can actually jump well across the map if he chooses to. And it was just overall an interesting experiment to understand how modern-day graphics cards render different kinds of systems. So don't confuse this with voxel rendering, which is a pseudo-volume simplification algorithm. This is simply a single approach that tries to optimize a complex scene.